Only one of these 4 Talent Cell power banks is what I would call a true 12-volt supply. Now, why do I say that? And what does that imply for your use case? And which one is the real 12-volt supply? Well, that's what I'm going to discuss in this video. Before I get into the details, this is not a sponsored video. I paid for all of these power banks myself, which is why I ask you, if you learn something useful from this video and you end up buying a power bank from Talent Cell or someone else or another kind of power supply, I ask you to use my links below this video where it says show more. You can use the specific links to particular power solutions, or you can use a generic Amazon link and shop around for whatever meets your needs. And that'll help support this channel so I can make other videos like this. And don't forget to like this video if you find it useful so other people can find it. And you might want to subscribe if you want to see other videos like this. So enough with the commercials, let's get to the point of the video. Portable power banks are very popular because they tend to be lightweight, compact power supplies that are very convenient to carry with you wherever you want to go. And Talent Cell lists a number of different applications such as LED lighting, closed circuit TV cameras, CPAP machines, portable DVD players, Bluetooth speakers. What interested me was the fact that they can also be used to power astronomy equipment used by amateur astronomers like myself. So back in 2017, I bought my first power bank, this 8.3 amp hour version, which I needed to take on a plane with me to view the total solar eclipse of 2017. Before I explain why many of the power banks sold by Talent Cell and other companies as 12-volt supplies really aren't 12-volt batteries and should be more accurately described as 11-volt batteries, let's take a look at what we've come to expect out of a true 12-volt battery. First, let's look at this discharge curve for a lead-acid battery. Its voltage drops below 12 volts after about 50 or 60% of the capacity has been depleted. Lately, lithium batteries have become very popular. Now, here are a couple examples of lithium iron phosphate batteries that I have tested and reviewed, and you can find the reviews of these and others on my YouTube channel. Now, while they're made in all kinds of capacities and by different manufacturers, they all share one thing in common. The discharge curve, which you see here for the batteries I personally tested, shows that the voltage stays above 12 volts for 90 to 95% of the total rated capacity of these batteries. So the bar has been shifted from 50 to 60% of capacity to 90 to 95% of capacity with these lithium iron phosphate powered batteries. Now, another very popular lithium power solution are the portable power stations, or some call them solar generators, like the ones I have here and I've reviewed also on my YouTube channel. Most often you'll find these are powered by lithium nickel manganese cobalt oxide cells, or NMC for short, because that lithium chemistry has the highest energy density, making for lots of power in a lighter weight solution than with lithium iron phosphate. Although you will find some models of these portable power stations that use lithium iron phosphate as well. Now, what do you get when you look at the voltage versus capacity on something like these? Well, here's the data that I collected on several different portable power stations, and you see that the voltage remains solidly above 12 volts, not for 90% of capacity, but for 99 to 100% of capacity, at which point the internal BMS shuts off the output. Whether it's lithium iron phosphate or lithium nickel manganese cobalt oxide, our expectation should be greater than 90% of the rated capacity will be available to us above 12 volts. Now, I'm going to go ahead and do a full discharge curve on all 4 of these power banks. And that's going to tell me what the voltage versus capacity is. It's also going to tell me the actual capacity of each power bank, and I can compare that against the manufacturer's spec. Now, instead of boring you with 4 bench level tests, I'm going to give you an abbreviated version of the test I did on this 6 amp hour one. And the tests are identical for all of them. It's just they will run different amounts of time because of different capacities. So let's take a look at that first test on this 6 amp hour power bank. Before I can do the capacity test, I have to make sure the power bank is fully charged. So I followed the manufacturer's instruction using the included charger and charged this to make sure all 5 lights are green and that the light on the charger itself goes from red to green, indicating, at least according to the instructions, that it's somewhere between 95 and 100% charged. That took probably about 6 or so hours to fully charge this. Now I have a load tester here, which I've used in the past when testing all of these other lithium power sources. It will record the voltage, current, power, amp hours, and watt hours as we discharge this power bank. And I will connect it with the 5.5 by 2.1 connector on the front. And this has Anderson power pole pigtails, which I made for this as well. All right, so we're gonna turn on the Talent cell. And we see with no load, the voltage is 12.4 volts. Okay, now we're going to raise the output current to 1 amp. Okay, 1.02 amps, and we're already down to 12.0 volts. Not a good sign. Let's let it run. I'll record manually. Okay, we're now down to 11.3 volts. Just a little over 1 hour. Okay, so we see that after a little over 5 hours, drawing just around 1 amp, this power bank shut down, supplying 56.93 watt hour. Now that's actually 85% of the spec'd 66.6 watt hours. So that's actually quite low. I would expect it to be at least 90% of spec compared to other lithium-based power supplies that I have tested in the past. So let me summarize the results of the bench level testing before I show you the voltage versus discharge curves. And I got to have my cheat sheet here because I don't have it memorized. So this 6 amp hour Talent cell battery, which has a 3 amps max, I ran it both at 1 amp and 3 amps. At 1 amp, it measured at 85% of its rated capacity. At the full 3 amps, it only provided 80% of its rated capacity. So I consider those fairly low percentages of capacity. The 8.3 amp hour battery, which is from back in 2017, this is rated at 6 amps max. I ran it at 2 amps. And it achieved 80% of its rated capacity, which isn't too bad considering it's 6 years old. This is the 12.8 amp hour battery, and its max is 6 amps. I ran it at 3 amps, which is half the maximum, and it achieved 99.6% of its rated capacity. This is quite good. And this one here is the 6.5 amp hour version. Its max is 5 amps. I ran it at 2 amps. So you can see, other than this one at 3 amps, I didn't push these hard in terms of current. And this one achieved 95% of its rated capacity. So these two performed quite well in terms of providing pretty close to or almost exactly the rated capacity. This one was disappointing. And this one I can forgive since it's 6 years old. Now let's take a look at the discharge curves themselves. And I want to isolate these 3 first, and we'll talk about this one later. So here are the discharge curves for these 3, and there's actually 4 curves. There's a curve for this 6 amp hour battery at 1 amp load and also 3 amp load. The first thing you notice is the no load voltage is 12.4 volts. And that's a tip-off that these are not actually 12 volt batteries, because if they were 12 volt batteries, the no load voltage would be above 13 volts, no matter whether it's lithium iron phosphate or lithium nickel manganese cobalt oxide. So that's the first tip off, that there's a problem with calling these 12 volts power supplies. Second, once we put any load on it, the voltage immediately drops down to about 11.8 or 11.9 volts. Now, if you take a look at the curve, you'll see that the voltage, after we've discharged only about 10 to 20%, depending on which power bank we're talking about, is now below 11.5 volts. And after we've discharged a total of 20 to 30% of its rated capacity, voltage is now below 11 volts. And the voltage drops even further, and then the remaining 30% of capacity on all three of these is actually below 10 volts, which is pretty darn low. Now let's take a look at the discharge curve for this particular power bank, which you see here. The first thing you notice is the no load voltage is above 13 volts, which is a good sign. As soon as you put a load on it, it drops just below to about 12.8 volts. And then the voltage remains above 12 volts for about 90 to 95% of its rated capacity. Now, lithium iron phosphate cells have a slight capacity above 3.2 volts, which you see in this typical curve for an individual cell, but it's not much capacity. So that's the reason why the no load voltage is higher than 12.8 and why the voltage drops down pretty quickly to 12.8 volts once you do apply a load. Now, how do we understand that difference in the discharge curves? Well, the difference is in the design between these power banks and this. Now, this power bank is powered by lithium iron phosphate cells, whereas these three and many of the others from Talent Cell are powered by NMC cells. Now you might say, oh, okay, that's the reason why these don't give you true 12 volts. No, that's not the case, because I showed you earlier that you can buy these portable power stations from Jackery, EBL, and other companies powered by NMC cells, and you get 12 volts throughout the full discharge curve with those things. So you wonder, why don't you get it here? And that has to do with the design difference between these power banks and this. As I said, this uses lithium iron phosphate, but it uses 4 cells in series. And so the nominal voltage of a lithium iron phosphate cell is 3.2 volts. When you multiply that by 4, you get 12.8. And if you look at the spec on the backside of this, you'll see it specs 12.8 volts. And the input voltage, if you look on the charger and on the back here, is 14.6 volts. That's the same design for lithium iron phosphate cells in series, charging to 14.4 to 14.6 volts as those lithium iron phosphate batteries I showed you before. So this is designed correctly to give you a 12 volt supply. Now these power banks have 3 NMC cells in series, and in order to increase the capacity, they put additional cells in parallel with that. So what you see on this power bank is 6 cells, 2 sets of 3 in series. So the 3 in series, multiply 3.7 by 3, and you get 11.1, which is what you see in the spec on the back of this. And you put 2 sets of those in parallel, and that gives you the capacity for 6 amp hours. The other tip-off is the input voltage. When you look on the back of the power bank, you'll see 12.6 volts. And if you look at the charger that comes with these, you'll see 12.6 volts. So why do I think Talent Cell only put 3 cells in series in these? Well, multiple reasons. So if you were to do 4 cells in series in 2 banks, you'd have to add 2 more cells. That would increase the cost. It would increase the dimensions of this, so this would get bigger, and it would increase the weight. And not only that, with 4 in series, like you have in some of those Jackeries and the EBLs, the voltage would be 14.4 volts. So they would also have to add an expensive voltage regulator in here. So to keep the cost down, to keep the dimensions down, and keep the weight down, they went ahead with a 3-cell design, which in my opinion would be fine if you call it an 11 volt power bank, not a 12 volt power bank. So the fundamental difference is not NMC versus lithium iron phosphate. It's 3 cells versus 4 cells in series. Now, why should I care how much of the capacity of the power solution is above 12 volts, since most 12 volt devices are pretty resilient and can take voltages above 12 volts and below 12 volts. But there are limits. As the voltage drops below 12 volts, some applications, some pieces of equipment just won't work as well. Now, if you're an amateur astronomer like I am, you may be interested in the power bank as a portable power supply to power lightweight mounts like these. Now, this is the mount that I took on the airplane with me, along with a power bank just like this, to film the eclipse in 2017. These mounts don't draw very much current. This is a Celestron SE mount, and this is an Ioptron Cube Pro. They draw less than 500 milliamps when tracking, and a little bit more when they're doing a high-speed slew. Now, just how low in voltage can this power bank go before these mounts become unhappy? Well, I tested these all the way down to about 10.3 volts, and both mounts seem to have no problem with that. In fact, I did high-speed slews on both mounts, and I didn't hear any straining or hesitation on the motors. Now, that's not going to always be the case even with a lightweight mount. I've seen reports on the astronomy forum called Cloudy Nights where people have had trouble with ZWO's AM5 and AM3 mounts with power bank. Now, if you go to a heavier duty mount, which has bigger gears and heavier duty motors, they're going to draw more current, and those may also have more problems with these power banks as the voltage sags. Even with lightweight, low current mounts like these, you also have to be careful if you're going to add other accessories to the power bank. So for instance, if you want to run a camera, you want to add a dew heater, maybe a mini PC, you're going to increase the current load, and the voltage is going to sag much faster than it will with just these mounts alone. And you may not get the capacity that you think you're going to get out of these power banks, and therefore the amount of time that you can run with the power bank may be a lot shorter than you think it will be. Now, I also tested my mini PC from Beelink, which operates on 12 volts, and I wanted to see whether the power bank with a voltage all the way down to about 10.3 volts would cause any issues with the mini PC. So I was able to turn on the mini PC, run the SkyX, connect to my camera, which is powered from a different power source than this power bank, and take and store images without any problem at all. So that seemed to work fine. I was quite surprised that the Beelink worked all the way down to about 10.2, 10.3 volts without issues. Now, that may not be true for your mini PC. I've actually seen other reports that ZWO ASI Air, which is actually a Raspberry Pi, doesn't seem to play well with these power banks as the voltage sags. So you just have to be careful to check the specs of your device to make sure that it will work okay as the voltage sags on some of these power banks that only use 3 cells in series to supply the power. The other thing to note is many of these power banks also have 9-volt outputs and USB, which would be 5 volts output. And those will work perfectly fine throughout the capacity because as we see, we have plenty of juice to handle 9 volts all the way down through the entirety of the capacity of these things. All right, so let's sum up. If the device you want to power with one of these power banks is actually fairly sensitive to 12 volts, you're not going to want to use one of these 3S designs. You're going to want to use a 4S design, and right now Talon Cell makes a 4S design using the lithium iron phosphate. And it's not only Talon Cell that sells 12 volt power banks using a 3S design such that you don't really get 12 volts out of it. So be very careful. Look for the spec. If you see 11.1 volts, if you see the charger is 12.4 or 12.6 volts, those are dead giveaways that it's not really a 12 volt supply. Now, if your application requires a true 12 volt supply, you're going to need to buy this particular Talon Cell, which is the 83.2 watt hours at 12.8 volts. Now, if you need more capacity than that and you want to carry on the plane, you can actually buy 2 of these, and you can carry on 2 of these, and that'll still meet the specifications by TSA. Now, if you do need more capacity than this and you don't want to buy 2 of these, Talon Cell does make a 24 volt power bank with 156 watt hours of capacity. And the nice thing about that is it also has a 12 volt output. And that 12 volt output, according to their specifications, will stay above 12 volts through the majority of its capacity. And that sells for $114. So that may be a good alternative if you need higher capacity and a power bank in a power bank format. Now you can also try a power bank from another company called Omni. So there's this Omni Ultimate, which has adjustable output voltages. And here's what that looks like. It has AC, USB, and you can adjust the voltages, and so you can get 12 volts output as well at 8 amps maximum output. And the only thing about that is it's kind of expensive at just under $400. Now Talent Cell also sells a true 12 volt, 12 amp hour battery like this one here, and that's the traditional battery form factor. Now this is not very large, can actually fit in the palm of your hand, and it weighs about 3 pounds, but it's not the nice form factor of one of these, and it doesn't have the convenient DC ports on it, so you have to make your own connections to it. But that will give you 144 watt hours of capacity in one small package. So I'll put links to all of these down below. And if you decide to buy something based on what you learn in my video, I really appreciate it once again if you use the links, because that helps support the channel. So don't forget to like the video so it helps other people find it, and subscribe if you want to see more of these. In the meantime, thank you for watching and hope to see you again.